In this video series, we will explore the history of quantum physics. Quantum physics studies small particles like atoms, molecules, electrons, protons, photons, etc. For example, suppose we want to predict the electron's location inside an atom. In that case, we cannot use Newton's equation or electromagnetic theory to predict the electron's location because small particles don't behave like particles or waves. Instead, it acts like nothing we have in day to day life experience. So, we will explore how the small particles behave and how it was discovered. It all started with black body radiation. So, what is black body radiation? If we take a block of wood and burn it, we can notice the fires red, orange, yellow, and more colors. So, the question is how do the different colors of fire appear? To find out why these colors appear when something is burnt is the black body radiation. We need more information to find out. To get more information, we need to conduct experiments. So let's take other materials like iron, aluminum, copper, bricks, stones, or anything and heat it and check whether we get the same color. German physicist Gustav Kirchhoff first did this research in 1859 and concluded that the color of the fire depends only on the temperature of the material heated. It does not depend on the material, size, or shape. So, for example, if we heat any material around 800 degrees Celsius, the predominant color is red, irrespective of the material used. Let's first understand light. In 1666, Newton first showed white light is the combination of all the seven colors using a prism. Until 1800, it was believed white light contained only seven colors. In 1800, with the invention of the most accurate mercury thermometer, William Herschel was involved in measuring the temperature of the light. Accidentally, he left the thermometer next to the red light. Later, he noticed an increase in the temperature and figured there was invisible radiation and later called it infrared radiation. A year later, in 1801, Johann Ritter discovered another invisible radiation on the other end of the spectrum and later called it ultraviolet radiation. Let's get back to the black body radiation. Gustav Kirchhoff wanted to explain how different fire colors appear from wood when heated. He imagined a hollow spherical sphere and a small hole in it and called it a black body. First, this object absorbs all the colors of the light incident on it. Then, the incident light enters through the hole, hits the wall, bounces back, and is finally absorbed inside the wall. So, it absorbs all the incident light on it. So, no light comes out of it. So, this object appears black. That's why it is named black body. When it is heated, it emits all the absorbed light. However, when the temperature is high enough, the predominant radiation is ultraviolet radiation. This is invisible to our eyes, so the heated object appears black. Next, he wanted to measure the intensity of each light color, plot a graph between wavelength and the intensity, and then derive the Kerr's equation. This is called the black body problem. Due to a lack of technology during those days, there was no progress. After 40 years, during the 1880s, latest inventions were made. German government and companies collaborated to develop the most efficient light bulb. The most efficient light bulb can be made from a material that emits more visible light and less heat. Everyone's attention was on finding the equation for the black body radiation. Wilhelm Wien worked under Otto Lemmer and was involved in developing photometers comparing light intensity and the black body investigation. During his free time, Wilhelm Wien worked on finding the blackbody radiation equation. Finally, he found the equation and sent it to Friedrich Paschen. Friedrich Paschen confirmed that Wien's equation matches his collected blackbody radiation data. But Otto Lemmer wants to check Wien's formula at a higher temperature and wide spectrum range. So he collaborated with Ferdinand Kuhlbaum and Ernst Fridsham and found discrepancies in the infrared region. However, everyone said there is only a tiny variation that may be due to experimental error. So again, they worked to eliminate the experimental error and still found discrepancies in the infrared region and disclosed the data to everyone. Friedrich Paschen checked at low temperature and confirmed that Wien's equation matches precisely. Finally, Heinrich Rubens said, okay, there are discrepancies only in the infrared region. So he developed a black body to check the infrared region at the temperature from 200 degrees Celsius to 1500 degrees Celsius. Found that Wien's equation does not match the infrared region. So Wien's law breaks. So based on classical theory, Rayleigh and Jeans applied the equipartition theorem to the blackbody radiation among different wavelengths. It predicted an infinite amount of energy in the ultraviolet region. Later, it was called an ultraviolet catastrophe. Thus, it is the breakdown of classical physics. Finally, Max Planck derived an equation for the blackbody radiation and sent it to Heinrich Rubens to check. Heinrich Rubens confirmed Planck's formula with available data. Ferdinand Kuhlbaum and Ernst Fridsham announced Planck's formula matches the data. Planck found the equation. It fits the data exactly, but that's not sufficient. He needs to explain how the different fire colors appear when we burn the wood. That means he still has to interpret the physical meaning of his equation. When he was trying to find the meaning, he could not explain it using the existing physical laws. Thus, classical physics failed. Then, how Planck's equation explained different fire colors that appear when the wood is burnt, and who helped to find the physical meaning, all we will see in the following video. Thank you. See you in the next video.